On behalf of the more than 30 researchers, fellows, and doctoral students of our Department of Interaction of Radiation with Matter, I want to thank the organizers for the opportunity of being present at this meeting. I invite you to visit this website, where you will find all the information about our lines of research and facilities. Our laboratory is located in an area of lakes and mountain forests in the Patagonian Andes in Argentina. In fact, we are at just 10 kilometers from the tourist city of Bariloche and at the same distance from Cerro Catedral, one of the most recognized ski resorts in South America. This, the first laboratory in Argentina dedicated to atomic, molecular and optical physics, was created in 1960 by Professor Wolfgang Meckbach. Wolfgang Meckbach was born in Frankfurt, Germany in 1919. During the war, he enlisted in the Navy, where he received the title of Naval Engineer and was later part of the submarine corps based in La Spezia, Italy. As luck would have it, in the submarine's first incursion, it was hit by a death bomb from an English destroyer. Thus, the war for Engineer Meckbach and his submarine companions ended when it has barely begun. As a prisoner of war in the United States, he was authorized to study at the University of Chicago. In May 1946, he returned to his hometown, where he married Gabriela Mack, his first and only girlfriend, and concluded his studies at Goethe University, where he received his doctorate in 1951. Since his mother-in-law was Argentinian, the young couple decided to settle in our country. He first worked at the universities of Bahia Blanca and La Plata. Then, in 1955, he accepted an offer from the National Atomic Energy Commission to create an Institute of Physics in Bariloche. In 1960, an old acquaintance of Meckbach from Chicago, Professor Samuel King Allison, visited Bariloche. Let us remember that Allison was director of the Enrico Fermi Institute in Chicago. At that time, Meckbach and a young group of colleagues were building an accelerator of up to 300 keV. Being aware of the spectacular resurrection of atomic physics happening in those years, Meckbach asked Allison if it would not be better to dedicate the accelerator to the study of atomic collisions instead of neutron physics. Allison's answer was enthusiastic. He said, "You are damn right. Why don't you come to Chicago to introduce yourself in that field working in my lab?" After these 2 years staying at the Enrico Fermi Institute, Meckbach returned to Bariloche with a great knowledge of accelerators and a grant of $66,000 from the National Science Foundation, destined for the new laboratory. During a second visit of Professor Allison to our ion beam laboratory, as it was called at that time, the first experiments were initiated. Unfortunately, in 1965, Allison died. His 400 keV Hofstad-Walton accelerator, nicknamed by him Kevatron, meaning a big machine for a low voltage, was closed in 1967, but it was not forgotten. In fact, our modest homemade accelerator, located 10,000 kilometers away, inherited the name Kevatron. Up to the present, the Kevatron has served to conduct more than 100 research projects and master's and doctoral theses, among them mine. But now, after 60 years of service, the Kevatron is about to be retired, and so am I, having worked in this laboratory for 4 decades. It is perhaps not useless to say that this short history shows that the value of an activity in research should not be judged by how much money it costs, but by the enthusiasm, stubbornness and resilience of people like Meckbach and his young colleagues who built the accelerator in the 1960s. The successor of the Kevatron is the Tandem, which was installed in 2010. This is a 5 SDH tandem accelerator from the National Electrostatic Corporation, with maximum terminal voltage of 1.7 MV, reaching a maximum energy of 3.4 MeV for protons and 5.1 for alpha particles. We have 2 sources. One is a source of negative ions by cesium sputtering, which can deliver negative ions of a wide variety of elements from solid cathodes. The other one is an alphatros, which provides ions extracted from a gas plasma excited with radio frequency, which pass through a rubidium environment. This source is used solely for the production of helium ions. During the last 10 years, this equipment has been growing and incorporating different facilities and end stations. The analysis chamber used for material characterization is a RC43, made also by NEC. It works in high vacuum and has surface barriers detectors to perform RBS and ERDA, one fixed and the other one mounted on a rotator holder. It also has a cerium silicon drift X-ray detector for pixel and flanges to mount sodium iodide scintillation detector for gamma-ray spectroscopy. The chamber has a lock stage which allows to introduce samples up to 30 mm wide easily and quickly. The sample holder has a micro-positioning ability in all directions and with angular orientation. This second line was completely designed and made in our laboratory 30 years ago. The chamber is intended to analyze energy, charge state, and angular distribution of charged particles after collision events between an ion beam and a gas jet, using a channeltron detector with 180 degrees of positioning freedom. We also have a reaction microscope to perform cold target recall ion momentum spectroscopy, which is still installed in the old Kevatron, as you can see in the picture on the right. But soon it will be moved to the Tandem. Finally, in the near future, a new chamber for surface science will be added to the Tandem. It will allow to perform Auger electron spectroscopy and wavelength dispersive X-ray spectroscopy. Going back in time, in the early 1970s, as the Kevatron was bearing its first fruits, a new accelerator of up to 100 kV was starting to be built. It was called Batrito, which in Spanish is a diminutive that means little Kevatron. The ion accelerator is an electrostatic one with voltages in the range of 2 to 100 kV. It has two types of ion sources, a radiofrequency one for ionization of gases and a solid-state aluminum silicate one for production of alkali ions. There are three collision chambers mounted in tandem. The first one is a high vacuum chamber for material irradiation. The second one is an ultra-high vacuum chamber with a time-of-flight scattering and recoiling spectrometer. The third chamber is similar to the second one but with a more complete surface analysis system, including ultraviolet photoelectron spectroscopy, Auger electron spectroscopy, low-energy electron diffraction, and electron energy loss spectroscopy. The irradiation chamber that I mentioned at the beginning has a linear driver for carrying multiple samples with a Faraday cap with an aperture of 1 mm for fluence determination. In front of the sample holder, there are deflection plates for beam sweeping and a carousel with slits of different forms and sizes to control the beam shape. For the analysis of these radiation damages, we count with two microscopes, one operated in air and the other in ultra-high vacuum. The atomic force microscope operates in ultra-high vacuum. Images with atomic resolution can be taken at different temperatures of the sample, in a range between 20 and 1500 Kelvin. The chamber is equipped with standard surface analysis techniques, with facilities for in situ sample preparation by means of annealing and spattering for surface cleaning, and it has a sample and tip introduction trap. On the other hand, the autoproof CP microscope from Park Scientific Instruments operates in air and allows to take images with nanometric resolution. The AFM operates in contact mode with 0.6 micrometer ultra-level tips. It is mainly used in the topographic mode to provide services to third parties. After the Kevatron and the Batrito, a low-energy accelerator facility was built to perform stopping power measurements with light ion projectiles with energies in the range of 1 to 10 kV. It has an electrostatic energy analyzer that can measure scattering angles up to 45 degrees, and by using self-supported ultra-thin film samples and the geometry of beam foil transmission, the electronic stopping power can be measured with a minimum effect of the nuclear contribution. Our more recent acquisition is a system for surface analysis by means of photoelectron spectroscopies bought in 2015 to specs. The ultra-high vacuum chamber is equipped with two photon sources, namely a monochromatic X-ray gun and a helium lamp. It also has a high-resolution hemispherical electron energy analyzer, a spattering gun for surface cleaning, and a rotatable sample manipulator with the possibility of cooling with liquid nitrogen. The system has a pre-chamber for fast introduction and remotion of samples. Another very nice and dear facility is a low-energy 30 kV ion accelerator with a penning-type ion source. It was manufactured locally as a personal project of a young researcher from our lab. As he was born in a city called Tucumán, he decided to call it Tucutron. And this has been a brief summary of the 6-decade history of our laboratory, of our people, and of our facilities. Now I would like to use these last minutes to give you some few examples of the use we make of this equipment. In its early years, our lab was mainly dedicated to basic research, and even today this is very important for us. Possibly the most surprising and unexpected result was the first measurement done in the 1980s of the double differential cross-section for the so-called capture to the continuum cusp in the single ionization of atom but fast ions. At that time, the trick was to use a cylindrical electron deflector. I remember the referee's comment saying that in the far south, with scarce resources but lots of imagination, the impossible has been measured. Our laboratory belongs to the National Atomic Energy Commission, so it is no wonder that it is our main customer. Let me show you some few examples. In the case of a loss of coolant accident in a nuclear reactor, metallic zirconium cladding rapidly reacts with water steam at high temperature. And of course you don't want this to happen, since it might result in an explosive mixture of hydrogen with air oxygen. This is why our collaboration with the colleagues working in that sector is so important. At the RA6 nuclear research reactor, which, as you can see in this photo, is just across the street from our lab, our colleagues in nuclear medicine are working on a boron neutron capture therapy for cancer, or BNCT. This, for instance, is a study done at our Tandem accelerator in relation with the stopping power of alpha particles in compact bone. We are also good neighbors with our colleagues in Patagonia working in archaeology and paleontology. And thus, we collaborate with them, as in this measurement of archaeological sample that I show you here. We also do the same with the Brazilian group studying the composition of meteorites. Our region is surrounded by volcanoes, especially in Chile. In general, they do not represent a great danger, but every so often they give us a surprise. This happened 10 years ago with the eruption of Pushehue, located 80 kilometers from Bariloche, and which literally covered us with ashes. One important environmental concern associated with volcanic eruptions is linked to the huge volumes of ashfalls that may deliver hazardous elements over large distances from the source. Thus, the group of the XPS specs collaborates with colleagues of the Earth Science Center of the Argentinian province of Córdoba in the analysis of the ashes of the most recent volcanic eruptions in our region. We are looking forward to the first visit we will receive within the framework of the Coordinated Research Project. They are Tabata, Andrés, and Eugenio from the Metropolitan Technological University of Santiago, Chile. Finally, since I have one more minute, I will end the presentation showing you that, in addition to our experimental facilities and wonderful colleagues, there is another good motive to visit us. The key phrase of the video that follows is "Quiero estar ahí," which in English means "I want to be there," that is, in Bariloche.